Alright, today we're looking at derivatives of inverses. On the first examples here, we are asked to switch the values of x and y for the following functions and sketch the graphs. So let's look at the first one. Our parabola here, or half of a parabola, we have a point at 0, -1, a point at 2, 0, and a point at 4, 4. Well, if we take those and switch them around, instead of 0, -1, we're going to have -1, 0. So that point would be right here. Instead of 2, 0, we'd have 0, 2. And 4, 4 just ends up being the same thing when we switch those around. So if we look at the graph of that, it should look kind of like this. Alright, I want you guys to go ahead and do this one on your own. Switch the x and y's and sketch the graph and see what you get. Okay, so you should get a graph that looks like this. Does anybody remember what it means when we switch the x and y values, what we end up with after that? Anybody? Anybody? Alright, when we switch x and y, we end up getting the inverse of the original function. Remember, to find an inverse, we switch x and y and solve for the new y, which we'll talk about in a little bit. But this is the inverse, this blue graph over here is the inverse of the original function. Right, so this one is the inverse of the original. And it's still a function. Over here, this is the inverse of the original function, but it's not an inverse function, it's just an inverse. It's still an inverse of it, but it's not a function, it doesn't pass that vertical line test. Oops. Right, so this one's an inverse, but it's not an inverse function. Right, because it doesn't pass the vertical line test, right? We can draw a vertical line that goes through more than one point. Now, if you look at these, you should kind of notice they look pretty much like the first one, only switched around a little bit. And what it is, it's a reflection over the line y equals x. So if we look at that line, if we take the original one and flip it over, or take the mirror image of it over that line, we end up with our inverse. Same thing over here. Take our original function and flip it over that line, reflect it over that line, and we get our inverse function. Just one thing to remember, and this is an example right here, this one, is that not all functions have an inverse function. Right, the key being the function part. Right, not all functions have an inverse function. You see in this one, the original graph is a function, passes the vertical line test, but then when we flip it over that line, y equals x, now it no longer passes that vertical line test, it's not a function. So this next part asks us, how can you tell if a function has an inverse function? Well, we can use what's called the horizontal line test. Right, for a horizontal line test, if a horizontal line goes through the original function at more than one point, then the inverse is not a function. So basically what happens here, it kind of cuts out the middle step. Normally we would look at this function, then take the inverse, so flip it over that line, then do the vertical line test. But really, if you were to do a vertical line on the inverse, if you flip it back over that line back to the original, that makes it a horizontal line. So we're kind of saving ourselves a step. So in this case over here, our first example, we could draw horizontal lines, and it's always going to go through just one point in this original function, never more than one. So the inverse of this is a function, because that means any vertical line over here is only going to go through one point. The second example, we can see if we draw a horizontal line, it's going to cut through this point in two places. Well, if we reflect that line over that line, y equals x, and we get a vertical line, we're going to see it goes through 2 points on the inverse function. So we know that's, I'm sorry, the inverse. So we know that's not a function. Right, another way now to kind of use a little bit of calculus, let's say we don't have a graph of our function and we can't do a horizontal line test. Another way we can figure this out is to see if it's a monotone function. So monotone, if you think about it, monotone is just the same tone, just one tone, it's not changing. Well, what it means here is that our function is kind of the same the whole time. It's either just increasing or just decreasing. Right? Our graph is either going up to the right the whole time or going down to the right the whole time. It never changes direction. Right? Just like monotone doesn't change. So monotone function is a function that does not change from increasing to decreasing, or vice versa. Right? So it doesn't change from decreasing to increasing. So a line would be an example of a monotone function. It's always increasing as we go to the right, or always decreasing to the right in this case. This would be another curve that would be always increasing. It never decreases. Same with this. Always decreasing, so that's monotone. But when it changes from increasing to decreasing, goes back to a couple chapters, what happens is we end up with a local minimum or a local maximum. Right? Local max here, local min there. So that's not going to be a monotone function because it's changing from increasing to decreasing, which then tells us it's not going to pass that horizontal line test. So this one is not monotone. Right? That one is not monotone, and our other 4 examples are. Right? To be monotone doesn't change from increasing to decreasing at all.